It's difficult. Do you hear me?
Yeah.
Okay. So, what you guys as developers are doing, it's so difficult. You create magic with your code and you build applications that help people all over the world. I do think that you are the heroes. So your time coding is so precious. Don't waste that on managing infrastructure, right? So with this session today, I want to inspire you to keep it simple. Okay? I want to show you that by using the built-in power in a cloud platform like Azure or AWS or Google or whatever, you can be even more successful. And using serverless technologies will make you even more innovative. So 20 years ago, when I was a junior developer, I was building monoliths. And it was so easy. I could just read my code, start a debug session, step through my values everywhere. But then my users start spreading all over the world, and the amount of users grew. So there is a problem with the monolith. It doesn't scale very well. So some years ago, I was part of a fantastic team, and we had a mission to build a system that could handle a lot of business transactions. Usually in these kind of systems, the database will be the bottleneck. We thought we should use CQRS architecture pattern to offload the database, separate the read side from the write side. CQRS, simply explained, works like this. The user makes a change in the UI. You send a command to the write side model. There you store your value, and then you send out an event that something has happened. An example of this is when you create an order and you send out order created event. You send these on a reliable messaging infrastructure, and then you have the read side triggering on those events and building up views or projections. And these projections are optimized for reading. Sometimes you even choose to have a special database on the read side that's optimized for reading and another for the write side. When the user queries the system, it will query the read side. So the architecture looks quite simple when I explain it like this, but we often end up with something like this. Usually you have some kind of domain-driven approach when you use CQRS, and it is not easy to get the bounded context and to actually get your aggregates in a good way. It's difficult. Also, modeling your events that you have to send out will be a little bit tricky, and you end up with a lot of different queues and maybe even 2 different databases that you have to maintain and manage. So, you start asking yourself questions also. What happens if an event is fired and the database update fails? How can I support a long-running business process? What happens when the event subscriber is not available? How can I be sure that the event is not lost? And how can I restore my system? So this is my agenda. I will show you a simple architecture where we use Cosmos DB and Serverless Azure Functions. And we will exercise the architecture and go through these questions and see how this serverless architecture will solve this for us in an easy way. First off, I will quote Martin Fowler. He says that event sourcing ensures that all changes to application state are stored as sequence of events. So I'm thinking, let's put all our events in Cosmos DB. And we introduce event sorting. So I have built this demo for you for this session. So it's an e-commerce system, and we're going to focus especially on the cart part. So we have a web UI where users can view products, add items, remove items from the cart, and do their purchase. When this happens, we will send these events and store them in Cosmos DB. And Cosmos DB has a nice built-in feature called the change feed. This is available out of the box, so you don't have to manage it. And the change feed will send out changes to your documents to subscribers. In our case, it's an Azure function. This Azure function will trigger, but it will also find out which specific cart are we dealing with, because our carts are made of durable entity functions. The durable entity functions is in general preview, so it's a new feature, and it's very much inspired by the actor model. So out of curiosity, how many of you have been working with actors in here? Quite a few of you, okay. But you will find this concept familiar. But what you need to know is that it's a stateful service. It keeps its information in memory. Okay? Under the hood, it stores states in a storage. It will also be silently offloaded from in-memory if it doesn't do any compute. And then whenever you signal the entity again, it will of course restore state and come back to life for you. Okay, but in memory. We also have a REST API function that will find the specific cart and ask for the items. And this means we don't query a database. And this also means that we don't have to do any joins or stuff like that, you know. So we also manage a long-running business process with a durable orchestrator. So a durable orchestrator main use case is to simplify the stateful long-running workloads for us. So when a user do a purchase, you typically create an order and you kick off a lot of different processes in your system. In our case, in my demo, I'm calling inventory and shipping. I have the code in GitHub. I will give you the link afterwards, so you can have a look. How does this relate to the old CQRS architecture? For starters, we don't have any commands, and we don't have a right-side model for our cart. We simply store the events in Cosmos DB, and then the change feed will send the updates. So we don't have any queues. Then we have the read side that doesn't have a database because we create the entities, which holds its information in memory. So when the user queries, it queries that entity. We still separate read from write, right? Let's kick off with our first question. What happens if an event is fired when the database update fails? And this is a very important question in this architecture. Because what will happen if we send out an event and we didn't store it in the database? The user will see items that does not exist. And even worse, it might not even end up on the order, right? We cannot have that. In our old system, we used a transaction scope. So in the scope, we wrote to the database, we sent on a queue. If something went wrong, we did a rollback. The transaction did a rollback. And nothing happened. And that's good, because then we stay in sync. But we're in the cloud now. We cannot have that. So what you have to do is you have to implement the outbox pattern. So when you write to the database, you write to an outbox table that something has changed. Then you have a process like a message relay, polling that. And if there are changes, the relay will send these to a message broker. But we're going to keep it simple. We don't have to implement the outbox pattern because it's there. Cosmos DB will automatically update state and publish the related, resiliently publish its related integration to our Azure function. So it's Cosmos DB and the change feed that will solve that for us. Next question, how can I support a long-running business process? And as you already learned, they're also called sagas or event-based workflows. An example is this. Order created, you send out order created event. Payment service picks that up and do some billing, send out build order event, and stock service picks that up, and so on. But the problem is here that you don't know how long this will take, and you need some kind of mechanism to actually keep track of this. Maybe you need to go to sleep and then trigger and see, okay, this is taking too long. We need to abort. We do have to do some kind of rollback. So to our rescue, we don't need to do this complex implementation because Azure Durable Orchestrator will manage this long-running process for us. So a durable orchestrator is actually implemented under the hood by using CQRS and event sourcing to accomplish this for us. And it's great. You have support for different use cases. One is the fan-out, fan-in pattern, which I have implemented in the code, in the demo. So fanning out is typically kicking off parallel processes, and then you fan in, you do some aggregation on the result. And you can do this with normal functions. You can fan out by sending messages on a queue or different queues, but the trick is to fan in, because how can you keep track of all those processes? And also the output, you have to store it somewhere. And then when you want to do your aggregation, you have to retrieve them, right? So this is being simplified for us. It's time to look at some code. I hope you can see back there. It's a durable checkout function. So when you use the function programming model, integrations to all other services are built in, abstracted away from you. And these are called bindings. And you can have input bindings, output bindings, you can combine them. So an input trigger is what's triggering the function, and we are listening to Cosmos DB. We have to set some attributes like the database name, connection string. And in our case, we need a lease. So a lease is a specific collection in Cosmos DB that keeps track of the subscribers to the change feed and their current checkpoint or last read event. We have an orchestration client, and this is used to call the orchestrator function, because this function is not an orchestrator function. So this function has a responsibility to actually subscribe to the change feed. And the reason I'm separating those into two is for scalability. Always keep your functions as small as possible so they execute as fast as possible. I have a challenge for you. This has already been spoken of today, so you should know this anyway. So here we're looking at the document or the events, and we're looking at the action. We're doing a checkout, so we only want the purchased ones. You're smiling. Yeah, so what happens? We have four different. We have view, we have add, we have remove, right? We only want the purchase one. What happens when this Azure function receives the other ones that we're not interested in? By now you should know, right? Anyway, it will execute. We don't want that. Because if we have our function in a consumption model through serverless, that means we get paid. We have to pay for every execution. So the reason I'm showing you this is because I want you to be aware that Cosmos DB change feed does not have message filtering support currently. But you're the heroes, right? You can create better code, create some message dispatcher or something better than my demo anyway. Last thing, we call the checkout function the durable orchestrator, which is this one. Here we have the orchestration trigger. We have the retry options. So we're in the cloud world. We have to be resilient because network failures will happen, right? So we have to retry. And this is built in to your Azure Durable Orchestrator. We create a list of different tasks to execute in parallel. In my case, I've done two mock-ups. It's inventory and payment. And we wait for all of them to finish by this. And then we do the aggregation. Next, what happens when the event subscriber is not available? You don't have to worry. We're keeping it simple, right? So the function instance will take back all previously owned leases immediately after start and continue from where it took off. So this is built in. So you don't have to have any retry logic that you write yourself, and you don't need any queues to be resilient here. So how can I be sure that the event is not lost is next question. It's because the change feed processor guarantees that it is resilient to user code errors. So the change feed processor is built into Azure Function, which is the preferred way of actually subscribing to the change feed. This is also available as an SDK that you can use if you don't want to use Azure Functions. And what I mean by resilient to user code errors, with that, I mean that if you write code in your function, that throws an error. The change feed processor will restart your function instance. And as you know from the last one, it will take back the leases and, kick off from where it left. And this is the reason that you have at least once delivery of your messages. You also have a guarantee of order within a logical partition key in your collection. Change feed processor is what guarantees resiliency. So under the hood, let's have a peek. So it's polling the change feed. If there are changes, it will send the changes to an observer, which is our Azure function. If all goes well, it will renew the checkpoint in the lease. And then it starts over again. Final one, how can I restore my system? When I'm talking about restoring my system, I'm not talking about restoring the database. I'm talking about if you get out of sync for some reason. And even though you have taken precautions, this is real life and, shit happens. So in our old CQRS system, we had a special management UI where we could set in events to, build up correct state again for if we, fail for some reason. But we have an event store, so we're going to replay that one. And we just use the start from beginning property in your function to replay everything and build up your state again. So you set this to true. That's what you do. This only works the first time on a lease. So if you want to do this, you have to create a new lease, a new collection. Otherwise, the change feed processor checkpoint will override. So I'm going to demo the application for you. So what we're going to do is we're going to do a modification in the code, and then we're going to do a restore, and we're going to apply the code changes. This is what happens in real time. Sometimes you need to apply your code changes to your state. So we're going to do some shopping, add items, do a purchase, and then when we view the cart, it will be empty, I hope. Okay, so then we remove the dispose part of the cart in the code. And if we do a restore after that, we should be able to view the items again because we have done a restore without disposing our cart. I actually forgot. So this is an implementation I've chosen. So in the architecture, we are disposing the cart when a user do a purchase, because I believe that when you actually create the order, we don't need the cart anymore. So that's actually a key thing that I forgot to say. Okay, let's see. So here I have the cart view processor. Okay, so I'm using Visual Studio, and I'm coding in C#. But of course, you can use Java, Node, Python, for instance, if you like. So by now, you know that we're listening to Cosmos DB trigger. Okay, But what this code does, this is the cart view processor, which means it's triggering to build up the cart. So in here, I'm actually looking at the action, and we had 4 different action: view, add, remove, and purchase. So in this case, we're having purchased, added, and removed. So when this happens, we're gonna signal the specific cart entity. So how do you keep track of the entity? Well, we send in an entity ID. So just to have a look at that, it's actually not very complicated. We have an entity ID, which take an entity name, and I have just coded cart. And the cart ID, in this case, coming from the UI, is just a GUID, unique for that cart. Okay, and then we send in with an action like purchased, add, remove. So the cart durable entity code is here. So we have an entity trigger with the entity name of cart that we just saw. Then we're looking at the operation name that we sent in. And if we have add, remove, and purchase. So add will just add this item in a list, calculate total amount. Remove will remove them, and so on. But this is the interesting part. As I said, purchase will remove the cart completely from memory and also from storage. So it's no longer there. I have set some breakpoints here, so we will see that those will kick in when we do our shopping. So this is my fancy UI. As you understand, I'm not a front-end developer. But anyway, here we have some products, and we can choose one. Let's take an expensive one, like a puffy jacket. So we add this to cart. And this means that we should break. You're laughing. We should break in the code. Here we go. So this means that we will signal the specific cart, right? I will release that one and continue. Okay, so now if we look at the cart, okay, here we have the puffy jacket, which is good. That means that the REST API is calling the specific cart entity for the information. So we'll do a purchase, and the purchase will trigger the disposal part. Here we go, delete state. That's good also. So it means that it will no longer be available. So I will just look in the cart sometimes because of eventual consistency. They could, So, but it's still empty. Let's see, what time is it? Okay. So let's go and do some code changes. Let's comment out, delete state. But as you remember, we also have to set start from beginning to true, because we want to replay everything. So commenting that one, and we need to have a new list. So Angela is your name, right? Let's call it Angela. I know it's because I had that in the comment just to make it easier. Very, very observant of you. Thank you so much. So that's what we have to do, right? Let's start this one. So I'm running this locally here now, but I do have my Cosmos DB in Azure. So this is why we have a little bit of latency here with the Wi-Fi. Also running locally, it's nice, but you can of course publish up to Azure if you like. So let's see if we get some nice logs telling me. It's always like this when you have a live demo, right? There we go. Starting to process change feed. Thank you. So let's cross our fingers, because this means that we should have the, was it a puffy jacket, right? Yeah. Oh, it's like magic, don't you think? Yes, I'm so happy. Live demos is, always scary. So, 5 minutes left. That's great. Since I only have 5 minutes, I cannot show you the goodies I would like to add. Because these are, my little bit of a favorite. We have an event-driven architecture. It's very easy to add real-time analytics and to show a dashboard. I don't think that Power BI is, the most funny thing, but my manager is the product owner and, the sales department, they just love it, dashboards that's, showing current users, revenue, stuff like that. Very easy. Also, number one thing to, that you want to have in an e-commerce site today is recommendations. So I would add like a cognitive service for this, which is very easy to use. 3 takeaways. Keep it simple. We tend to over-engineer. We complicate things. Even though this example and the architecture I showed you maybe don't fit everywhere, but I'm sure that you can find use cases where this will be a good fit. Use the built-in strength of the platform, Azure, AWS, Google, whatever, but do not manage infrastructure. Skip that. Use serverless. Don't code your integrations and don't even manage your scaling. And you will become so successful. With that, I want to thank you for listening.